one to left. It's fine. Okay, so again, you guys can download the presentation from the Slack channel, general channel. If you guys have any questions, please do ask them. I do cover some things that are not in the book. How many of you guys are familiar with Big O notation? Okay, cool.
Familiar.
So you guys can teach that to me then. That's wonderful. Okay. So today we're going to be covering hash tables, dynamic arrays, string builder, and then again, Big O notation. Just the basics of it. I'm not going to go into detail. So let's go. So what is Big O notation? To begin with, most of you guys as developers won't really use this on your day-to-day.
Hold on.
No. As a web developer, you normally don't.
Web developer.
Right.
Okay, okay.
You're talking about software engineer. That's different. Right? Don't get up and try to punch me over here. Calm down, Baz. Down.
Just say it.
Yeah, but either way, it is very useful to understand. It gives you an advantage against the competition, right? So, wonderful to understand. So again, Big O notation is used in computer science to describe the performance or complexity of an algorithm, okay? We do have some slides that will show you some images that hopefully will have it make more sense. Big O specifically describes the worst case scenario. It can be used to describe the execution time required or the space used in memory or on disk by an algorithm, okay? Does that make sense? Okay. So here is an image. And it's,
just a point.
Yeah.
Because there is a difference between that and time complexity.
what's the difference?
Well, so like one is how many cycles, CPU cycles that it takes to complete whatever, and the other one is how long, because you could have two different Big O's that are you know, the same or similar as far as their computational cycles, but just as an example, let's say going out and getting something from a network location or from I/O or something like that, time complexity on that is going to be quite a bit different than simply the number of operation that it takes to get that done. And the only reason I mention that is because in that description that you threw up there, I heard time, right? Like, yeah, time required. They would be two different things, right? Like,
So you're talking about cyclical, right?
well, sort of.
Because this one's referring to, in the context of algorithms. I don't know if that makes a difference.
Well, there is a difference between, you know, Big O and the time complexity. They are two different notations. But, all right, let's just keep rocking.
You sure you don't want to explain it? Because
I do. I mean, well,
I do.
I kind of did.
Come on, let's do it.
I kind of did. I mean, again, a single operation does not necessarily take the same time, right? But your Big O notation on that would be the same because they would both be O of 1, right? Or O of n or whatever. But when you measure time complexity, then you measure the operation complexity of it. So, and that often makes a difference. I mean, a lot of times, especially, again, not so much in web development, but when you're dealing with Big O stuff, you do both of those notations. You check your Big O and whatever, but then you also look at your time complexity because that often is a deal breaker regardless of what Big O is.
okay, so hopefully it'll be more aligned to what you said once you see the other slides.
Sounds good.
So
let's rock.
We'll see. So here we have a chart that kind of denotes what's efficient and what isn't. So for example, here at the bottom, we have O of 1, and then we have O log n. Okay, so we do have some slides that will kind of explain what these are. Not all of them, but the most basic ones. Okay. I also want to throw this in here. These are the common data structure operations. It also shows the time complexity like Vas was talking about. Average, worst, and then the data structure. Its efficiency is denoted by the color, so green being good, yellow being all right, and then orange, you guys can guess, right? Not very good. So if you guys do have a chance, you might want to take a look at that. You guys can see that hash table seems to be the quickest, right? What do you think?
The quickest, what do you mean?
As far as data structure goes? Look at that?
Oh, okay. You're talking
Come on,
about
guys, you gotta pay attention if you're gonna.
Alright, yeah, I'm with you.
Thank you.
I'm just, you know, an array is usually a go-to as far as quick as access.
Yeah, I guess it depends in context,
Yeah.
right? Well, that and language.
Depends. I mean, if you're talking about memory locations, array is hard to beat because you don't even have a lookup at all. I mean, even with a hash, you have a lookup, right? Like it literally is. It's still old
So the
one, but
only
you still
reason-
actually have to check
The only reason I said it depends on language is because I was thinking about, you know how in Java arrays have a set length? So in JavaScript, they're dynamic.
So
Right?
you have to essentially go through the list, right?
Yeah, so anyways, we'll see.
You're right.
We also have, I also dropped this one in here, array sorting algorithms. Just thought it would be useful for you guys to take a look at when you guys get a chance. Again, this is not in the book, so.
Is there examples of these algorithms anywhere?
I'm sorry?
Are there examples of these algorithms?
Yeah,
anywhere?
so we're gonna cover a few of them. So for example, O1 describes an algorithm that will always execute in the same time or space, regardless of the size of the input data set. Okay? And we do have examples on these slides. So, can someone open the door? We should all look at him.
Well, look who decided to show up.
We just say his name. Okay, so did you guys take a look at that? O1 describes an algorithm that will always execute in the same time or space, regardless of the size of the input data set. Okay, does that make any sense? Okay, we do have an example here. You guys can refer to this again in the future. Okay, all of n, and again, Felipe, if I'm butchering anything, please tell me something. Don't just smile at me. All of n describes an algorithm whose performance will grow linearly and in direct proportion to the size of the input data set. Okay, does that make sense? Does
Yeah.
that sound correct? Cool, and we do have an example here. Anyone know Java?
C.
See? Okay. Well, it'll be used for you, Bess. Okay,
Wait, you say this is Java?
and the back.
That's not Java, that's C#.
See? You sure?
Yeah, Java has 4, and then the colon between its list and its whatever, and it also is Boolean, B-O-O-L-E-A-N in Java.
So what is this?
C#.
C#? Okay.
Yeah, but as you can tell, very similar, right? Very similar.
We're gonna have to make that possible.
Also,
right?
well, yeah,
Okay, cool.
but yeah, keep going. You're good.
So O of n squared represents an algorithm whose performance is directly proportional to the squared size of the input data set. And we have a big example for that one. So this is common with algorithms that involve nested iterations over the data set. Deeper nested iterations will result in O of n to the 3rd power, O of n to the 4th power, and so on. Okay? I don't think that's gonna make any sense without the example. So okay. So you guys can see, first of all, there's 2 levels here, right? There's one for loop, and then there's one nested inside of that for loop. Okay? Do you guys see that a lot?
Well, you shouldn't.
You shouldn't, right?
Yeah,
Right.
that's
So
bad.
you should avoid doing that. So right off the bat, that's something that you know already you should avoid doing. So you can imagine doing this for, say, a list of thousands of elements, right? It'll take quite a bit of time.
Right.
So
And worse is that it's not directly dependent on your input, right? If that varies, it doesn't go up linear at all. So for projecting scale, whenever your stakeholders and whatever say, well, you know, is this going to blow up our computers or is this going to whatever? you can't give them a projection with that, because you don't necessarily know what the input is, as opposed to some of the other big O stuff. If you do know, or it's regardless, right? It's like, well, this scales with whatever number of input we have. But if you're doing nested for loops, especially if it gets further than that, you get variations that you can't account for. Well, if its input is bigger than this, well, now we're moving up at an exponential rate instead of linear rate.
And what you're talking about,
Right.
this right here.
Right.
So this becomes important when you start doing work with like, for example, now I've been doing some work with like search. That's where it starts making sense. And you start looking at these things. Okay, so we have O of 2n denotes an algorithm whose growth doubles with each addition to the input data set. The growth curve of an O 2 to the n power function is exponential, starting off very shallow, then rising meteorically. Can someone help me with that word?
Meteorically.
What April said. Okay, an example of O of 2 n squared function is the recursive calculation of the Fibonacci numbers. How many of you guys have seen that before? Fibonacci sequence. Okay, perfect. I think it's something we all cover. Okay, so here's the example. Anyone want to take a stab at this one?
What it's doing?
Yeah.
I know I just went through this, it's recursion, so it's
Yeah. Let me
getting
see.
all of the values, and then it's gonna go back through and fill it in as it goes, so it kind of goes up and then back down and then back up again.
But important part there is that it doesn't return until it actually
Correct.
gets done.
It has to do the whole-
Your stuff is, yeah.
Cool. So one thing we're not covering in this talk is logarithms. Have you guys heard of those? Yeah. Okay. So we will have a talk based on just this. We'll go into detail for that. The only reason I put this in the presentation was because it does mention it in some of the items that we're going to be covering, and I figured just so you guys have some point of reference, right? Okay. So chapter 1 deals with arrays and strings. Okay. Okay, so hash tables. How many of you guys have heard about hash tables before? Okay, perfect. In computing, a hash table is a data structure that implements an associative array, abstract data type, a structure that can map keys to values. A hash table uses a hash function to compute an index into an array of buckets or slots, from which the desired value can be found. Okay. For those of you guys that use JavaScript, have you guys heard of the map data type? Okay. So we'll talk about that later. So how is a hash table built? A hash table is made up of 2 parts: an array, the actual table where all the data to be searched is stored, and a mapping function known as a hash function. Okay, and I do have some slides that have images that hopefully will help make it sense. Okay, so the hash function. The hash function is a mapping from the input space to the integer space that defines the indices of the array. In other words, the hash function provides a way for assigning numbers to the input data, such that the data can then be sorted at the array index corresponding to the assigned number. Okay, so let's take a look at that image right here. So you have a hash table, right? First, so we have an example, and we're going to go through it. So first, we want to start with a hash table array of strings. We use strings as the data being stored and searched in this example. Let's say the hash table is the size of 12, right? So we have 12 right here. Okay, does that make sense so far?
Mm-hmm.
Okay, cool. So as it is right now, it's just empty, right? Okay. Okay, so this is our hash function. Okay, this hash function takes this string as an input. The returned hash value will be the sum of all the.
Why is there an asterisk?
He switched to C++.
Okay.
Yeah, don't ask me about these
Yeah, he
languages.
was
These
right,
are the
man.
examples
He
that I
used all
got.
the languages in here.
Okay.
Do you guys ask for different languages?
You
Here you
got
go.
it, man, you got it.
You're
Keep
welcome.
going.
So is that a splat? What is that?
That's a
pointer.
pointer.
It's a mistake, is
Listen,
what
I
it
didn't think
is.
there were- I didn't think there were pointers in Java or JavaScript.
Just kidding, Baz, calm down.
It's a reference to a
Very
mistake.
important.
When you do that talk, we'll ask those
Okay,
questions.
yeah. Oh, I'm not doing the talk on C++, F that.
Okay. Interesting. So the, so the return hash value will be the sum of all the ASCII characters that make up the string mod, the size of the table. Okay? Anyone want to take a stab at what it's doing? Hey, there's comments in there. Okay, so right here, on line right here, it's making sure a valid string is passed in. Okay? And then right here, Scott, you have a question? Want to say something?
It's not,
Well, some not initialized, it should be initialized to 0, right?
I'm sorry?
you're gonna get an error. You can't do,
Bass, you can take over. One.
No, keep going.
No, you can't-
Wait for his
you're
question.
gonna get a type error. You can't do a plus equals for integer and character.
What line are we talking about? This
In
one?
C, it don't explicitly cast it.
This one?
You have to cast it.
No,
In
C++.
C++.
No, C will do implicit cast.
Yeah, but in C++,
C++,
you have to cast it or you get a
Yeah,
error.
C++ will probably get there. C will implicit cast will allow.
That one, yeah.
Okay. So
Wait,
it might
hold
know.
on. You're saying that you can't do plus equals pointer string?
Okay, the pointer string is pointing to the memory location
Right.
that holds that value, so
Of
it's
that
gonna
character.
return.
No, well, the
No,
important
that's
part
the
is that's the
reference.
character.
Yeah,
So
actually, no,
and
you're
it,
right,
and it
it's
holds
0 to
it-
256.
Yes, it holds an index.
So it's a
and it can
numerical
do so.
value, you're right,
That's
sorry.
why it works.
Is this hashing over how many characters are in the string?
So, first of all, what did we learn right there?
Well,
What was it?
the pointer, the reason this works is because str is, the pointer is going to a character, and
Okay.
characters have an int value.
Okay.
That's the only reason you can plus equal it to sum, which is an int.
You actually have to cast the number as a character to get it to print a letter on the screen as opposed to just printing out the ASCII value unless you specify it.
So this is right here. Sum of all the characters in the string. Right?
Right.
Yep.
After that, it returns to some mod, the table size. Okay? So we have right here. So we have this the hash table, right? As soon as we pass it in, we called it hash, right? Keep thinking I have my cursor. So right here, and we're gonna use it here to a string that says Steve, and 12 is the size of the hash table, right? So that's going to return 3, okay? So the 3, we're gonna use it as the index, and we're gonna input it in there, right? So the next one is a string called spark. Again, hash size, table size, and it's gonna return 6. Okay, so that's the index we're gonna use now. And we're gonna put spark in there. Okay, does that make sense so far? April?
I have no idea why Steve is 3 and Spark is 6.
Oh, right, okay.
So what if it was like Vesti?
So we have this function right here, right?
Yeah,
So this is our hash function.
correct.
All that it's doing is producing an index number for us, right?
So, just to jump in here,
Yeah.
you're passing into this hash function the character array of Steve.
Correct, which
Right.
is 5 characters.
Yeah.
No, it's adding up the
The ASCII
The
values.
character
ASCII value of the
values,
characters.
right. So,
And
so
then-
S equals, actually, I don't even, I'd have to look it
So
up.
whatever
It's
those, like 65, whatever,
It's between
Something.
70
and then it's doing
whatever.
the modulo of that
Yes.
to 12, okay.
Right, but, and the
I
important
just didn't
thing,
know where number 3 and number 6
the
came, that's
important
where I
thing
was.
is that it doesn't really matter because it's going through and getting this number and where to put it, and meaning that it can do the exact opposite to get that back out,
Right.
right? So that's like the ideal in hash.
But what if you have multiple values
Ah,
that have the same
conflict
return?
resolution, yes, if you put in, or try to put in
So-
2 Steves or
Collusion?
do something
Yeah,
that came
we're
back.
gonna
and
go over
said-
that.
Yeah,
Yep.
What if you
I know that's coming. By
Perfect.
the way, that's why prime numbers are so important, and if you find a new one, you can get like $500,000 just by finding a new prime number, because the actual hash dictionary stuff that they use, those are, for encryption and stuff, are like ridiculously valuable. I mean, to you know, people that use them, but that's kind of why I come up with it.
You just found a new one like
Well, it's not
2 weeks
super.
ago.
Well, right, but it's not right. It's not easy. Otherwise, everybody would do it right. Like, so anyway, yeah, it's
So,
an
April, does that make
interesting
sense?
thing.
Yeah, yeah, I just
Okay.
didn't know where, I wasn't, yeah. I didn't know it was the ASCII values. I thought it was
Cool.
like the length of the string.
Right.
So what he was talking about, collision, well,
Yeah, it's in the next slide, so.
right here. Cool. So we had Steve. He's index 3. We did Spark. What happened?
Nothing. I just in 3, Steve was, you know,
Calm down,
having
right.
this collision. It's funny.
Okay. Spark. God damn it.
It's funny.
Spark, it's at index 6, right? And then we have the string that says notes, and it comes out to 3, right? And we try to put it in index 3, so what's going to happen?
Collision.
Collision, right?
Right.
So, hash table collision. A hash function doesn't guarantee that every input will map to a different output. In fact, there's a section in the book that talks about how it shouldn't do that. There's always the chance that 2 inputs will hash to the same output. This indicates that both elements should be inserted at the same place in the array, and this is impossible. And the phenomenon is called collision, right? Now, to solve collision, there are many algorithms for dealing with collisions, such as linear probing and separate chaining. Don't mind the space right there. While each of the methods has its advantages, we're going to discuss separate chaining, okay? So, separate chaining. It requires a slight modification to the data structure. Instead of storing the data elements right into the array, they are stored in linked lists. Okay? Each slot in the array then points to one of these linked lists. Okay? Have you seen that before, Beth?
Mm-hmm. I've written it before.
So when an element hashes to a value, it is added to a linked list at the index in the array. Because the linked list has no limit on length, collisions are no longer a problem, right? So if more than one element hashes to the same value, then both are stored in that linked list. Okay? So let's try that. So we have the modified table for separate chaining, right? So we have a hash table, and then these are all empty linked lists, right? So we're going to add elements to the hash table, which will cause collisions. So here we add Steve. Remember, it was index 3, right? And then we added Spark at index 6. And then we added notes at index 3. But now it's inside the linked list, right? So now there's no issue there. Does that make sense?
Mm-hmm.
I don't see a lot of yes.
How do you differentiate between them?
I'm
So
sorry?
when you look it up, you have to search the linked list to make sure it's there.
Oh, so there's a linked list for each element in the hash table.
Yeah.
Well,
So
yeah.
each one of these is a linked list.
Okay.
Right.
I thought you meant to turn
So
the whole
that's
hash
gonna
table into
slow
a-
down the processing, cause then it hits 3 and it has to bounce
You're
through.
right,
three, right?
which is why hash tables are not really O of 1.
Mhm.
They are considered O of 1 because the hashes are so good now
Assuming
that
you
you
would get-
almost never actually get collisions. Like the built-in hash ones are so good that you
Yeah.
almost never do. But if you ever have a collision, now they do jump down the leap. That's why it's still considered O of 1. So like when you're doing your, but it's not quite O of 1.
The book throws in there that you might be, if for some reason you're super unlucky and you get it to where like all of them go into the same index, and yeah,
Then you're-
you have
yeah.
a problem. So.
But then I mean, again, your algorithm, your
Right.
hash algorithm is probably not real good, but
Right.
yeah. But even honestly, like
So-
those are very far
Wouldn't it be-
cases. That
Wouldn't it be faster to use a 2D array or use an array instead of a,
I think it depends on the
Linked list?
context, right? On the problem you're trying to
Because-
solve.
because arrays are always
Well,
contiguous memory, but a
But
linked list.
but in arrays you have to know what index you're looking for, right? Like
Just
this,
dynamic
you
array.
well, but the thing is with an array you have so to go directly to a memory an index, right? You have to know which index you're looking for. With a hash table, you just have to know what key you're looking for. So, for instance, say you are looking for through names, right?
Mhm.
You would have to say, oh, well, here I have an array, and I want to go to Steve or find Steve. Well, I still have to look down through that and then worse, compare streams in each one of them to find, oh, this is index
But
whatever.
that would only be if you've had the element in your hash table.
No, hash table set, you're talking about arrays.
Well, no, I'm saying you turn each element in a hash table into an array if there's multiple, instead of
Okay.
using a linked list.
The reason that you don't do that is because arrays have a fixed size, and you don't know. And if you didn't do it with a linked list, every time that you had a collision, you'd have to create a new array, put it in there, and worse, because of the slowness of it, copy each element of the old array over with the new link. And
Yeah.
that is quite expensive as opposed to a linked
But
list.
once it's done, it would be a lot faster to look
But
stuff
you don't know
up.
how many collisions you're gonna have, and you don't know how many long. With that, I mean, that is the one big advantage of a linked list over something else, is that you can add and remove instantly, right? Because it's just a pointer to the next one, right? Like
Yeah.
it's instant add or instant pop off, right? Yes, searching is quite slow because you have to go down the list, but the reason they do it on there is because otherwise we're constantly every collision creating and copying new arrays.
Yeah, no,
so,
dynamic
yeah.
arrays, they're very intensive to modify,
Right.
but once they're created, I was just thinking it would be much faster to sort through if there's collisions.
Well,
So-
right, but you're not sorting through that. You're literally just hopping
Water's
down
going.
the list. And the idea behind hash tables is that you're hopefully not going to have very many collisions. So, like, I think it's the greater good, right? Like, more often, I'm not going to have collisions, so it would be better to have it as a linked list than it would be to do arrays.
Okay, so how is searching effective, right? Because we modified the structure, right?
Right.
So once we have our hash table populated, a search follows the same steps as doing an insertion, okay? We hash the data we're searching for, go to the place in the array, look down the list originating from that location, and see if what we're looking for is in the list, okay? So did you guys understand hash tables? Okay, you guys won't really understand them until you actually use them. It'll make more sense then, right? You gave me a lot. I was gonna do this, I'll fall. Okay, anyway.
Drinking is hard.
Thinking is hard, yes, it is.
Yolan has a drinking problem.
And then, oh, come on.
Anybody old enough to remember that airplane?
Yeah. He thinks we were talking about
I know, I
alcohol.
know.
Anyways, resizable arrays. In some languages, arrays, often called lists in this case, are automatically resizable. Okay? The array or list will grow as you append items. In other languages like Java, mistake language. Arrays are fixed length, not just kidding. The size is defined when you create the array, right? So how many of you guys have used Java before? Okay. Do you guys like have you had issues with the arrays before?
Like what?
You just have to know what you're using them for.
Okay.
I will say, so in languages like C#, there's the class list, which actually uses arrays under the hood, but it does all of the maintenance for you,
Cool.
which is really nice because if you have, if you have an array of 10 elements and you need an 11th, instead of just creating one more and doing all that copy, it'll create like 20. But your length is still the size of whatever the stuff in there. So it automatically does that extra stuff for it. Thus, you get the speed of arrays, but the ease of
Right.
adding.
Very cool.
It's
And
easy enough to create your own linked list if you know how to manipulate arrays.
But that's different than a list is different than a linked list. List is like an array list. So using arrays under the hood, but not a linked list. They are two different things.
No, I'm just saying, if you're good at working with arrays, it's easy enough to write your own class to create your own linked list out of, never mind.
Okay.
So another concept that is covered in this chapter are array lists. An array list is an array that resizes itself as needed while still providing all of one axis, right? A typical implementation is that when the array is full, the array doubles in size, okay? We have an example here. So according to my notes, this is Java.
It is.
Okay, perfect.
No array list in C#.
back into the book. Okay. So when you need an array like data structure that offers dynamic resizing, you would usually use an array list. Okay. Does this look familiar at all to anyone that uses JavaScript, for example? No, right? I think for example, when I was telling you that coming from JavaScript and going over to like Java, you're used to having an array that just does whatever for you. It's kind of torture. So, yeah.
I'm finding even just some of the methods that are available to strings and arrays from Ruby that aren't in JavaScript. It's like, oh, are you kidding me? I have to do 2 extra steps. Why?
Yeah.
It's such a simple process.
Yeah. But I mean, it's nice to see those different nuances in different languages, right? So,
Yeah.
Okay, the other concept that is covered in the book is string builder. Imagine you were concatenating a list of strings. So I can say that word, but I can't say the other one. That's wonderful. As shown below, what would the running time of this code be? So imagine you were concatenating a list of strings, as shown below. What would the running time of this code be? Let me zoom into this code because it's pretty small.
You asking for the big O?
Yeah.
O-N?
You said O-N?
O-N, depends on how many words you have in it, right? I mean,
So on each concatenation, a new copy of the string is created, and the 2 strings are copied over, character by character.
Oh, I thought you were using string code.
Okay.
Oh, yeah.
So the first iteration requires us to copy X characters. The second iteration requires copying 2 times the characters. And the third iteration requires 3 times and so on, right? So what do you think the time is?
Terrible.
Terrible, right? I think that's what we're trying to establish. So let me zoom out. Okay. So here's the problem. Okay. Again, on each concatenation, a new copy of the string is created, and the 2 strings are copied over, character by character, right? The first iteration requires us to copy X amount of characters. Okay. So in the next slide, we're going to cover the solution. Okay. And yeah, this is what it comes out to. Okay. Anyone want to tell me what that says? I couldn't figure the little.
O of X in 2? What is that? What is
Squared?
your X?
Here. So it says the total time therefore is 0 parentheses x plus 2x plus and so on. And then it comes out to O of xn squared. So again, it's all in the book. So here's the solution, right? The string builder. It can
X
help you.
being the exponent? Is that what? I
Sorry?
don't know.
It was the length.
This?
Yeah, the next slide.
I've never seen a big
The next
O of
slide.
X in 2.
On
The
the next
2 would be
slide, you
squared.
defined X.
Oh, so X is like you're suggesting that's like a
Yeah.
variable. Okay.
Yeah. Okay, the solution would be string builder, right? It can help you avoid this problem. String builder simply creates a resizable, and again, string builder is an approach, right? It's not something you're going to look for in your programming language as a method or something. It simply creates a resizable array of all the strings, copying them back to a string only when necessary, right? And again, here's the example. Okay, so let me reread that again. String builder simply creates a resizable array of all the strings, copying them back to a string only when necessary. Right? Does that make sense? Okay, I hope so, because the next slide is very complicated. So it's exercises.
That is complicated.
Okay. So Beth, start doing those squats you were doing last time, please.
Oh man, because that's gonna give me the best partner.
Okay. Okay, so for those of you guys that brought your laptops, you guys can use Code Signal. It has challenges to help you prepare for interviews. You can access
gonna do
all
it
the
in
challenges on this link right here. Okay? I'm gonna go ahead and post it on Slack, and you guys can access it from there.
Cool.
We also have some challenges in the presentation itself. We have one called the Palindrome Permutation, and then a few others. If you guys want to give those a try as well.
For sure,
Okay.
for sure.
again, make sure you guys pair up,
C#.
and if you guys need help, let me know.
Okay.
Yeah?
I mean, whatever, it don't matter.
You'll be teaching me either way.
Cool.
No, I doubt it. I haven't even looked at